Well, welcome geology class. This is the first in a set of instructional videos in how to complete the groundwater lab. I'm trying to keep it short but full of information so you can rewind and replay as need be to understand what the question is after. You have by now the list of questions. We are starting with question 1A and B from the groundwater lab on page 173 of your lab manual. And that particular question surrounds this particular map of a portion of Nebraska. So I thought I would show you what it looks like. So this is the portion. Let me back out so you can see where in Nebraska. This is called the Sand Hills region of Nebraska. And if you look at it from far away, you can get an idea. So we're in that sort of that this portion of western Nebraska. And as we zoom in, you can definitely see what looks like ripples in the surface. And this portion of Nebraska is the Sand Hills area of Nebraska. This is an aeolian dominated surface feature that's mainly formed by wind as wind moved sediment around. But we're looking at a portion of Nebraska between Ellsworth and Lakeside right here. Lakeside, Nebraska, I'm sorry, right here. And if we zoom in on Ellsworth, just to give you an idea for what it looks like, it's not a big town, I'll grant you that, but there's good people living there. And if we look at it, you can just see, well, you can just see there's not that many houses in Ellsworth. But if you look at it, they do have one main business, and so let's just zoom in on that. Take a little peek. I gotta go here because I just think that this is a place that needs to be visited. There we could go to Cowpoke Haven. Morgan's Cowpoke Haven, established in 1898. That'd be pretty cool. So anyway, if we look at this region though, there's another feature that stands out, and that is all the little ponds, the little surface features, surface lakes that are in this whole area of Nebraska. Okay, and this is a pond, this is a pond, this is a pond, pond. Now in this area the wind has scooped out because there's loose surface sediment. This isn't agricultural country, this is rangeland, this is where cattle are raised. And so the wind has scooped out these ponds, and these ponds are actually the groundwater level. And so you have a surface feature that tells us how where the groundwater is at. So that it's flowing beneath the surface here, and it pops up in these ponds periodically that have been scooped out. And so your job is going to be to go to this map of that portion of Nebraska. Again, here's Ellsworth here. Here's Lakeside here, and you're going to answer a series of questions. The first question, if you look at it, is to draw a contour map, but not a contour map of the surface, a contour map of the groundwater table. Where beneath the surface, how far down would you have to dig before water would fill the bottom of your hole? Okay, well, if you're at the lakes, it's at the surface, but if you're, like over here around the lake, where would you have to go? This is a nice little hill. How far down would you have to dig before you hit groundwater? And so we're going to use these surface lakes as elevation points, as data points for the water table. So this is where it's at the surface. It would be underneath the surface next to these lakes. And I want you to use these as surface data points to draw a topographic map of the water table. I'll try to demonstrate using this particular feature. See, shapes. Yeah, and so I'm going to draw one on here, so a couple of them on here. So right here is Kennedy Lake, and I'm going to flip to that one, and that's at an elevation of 3906. I think you have that in your lab manual. And here's Haynes Lake at 3904. And I think the instructions tell you to do 5-foot intervals. And so we could go right here and draw a line like so, kind of right between Kennedy Lake and Haynes Lake. Okay, and then over here we have 3903, 3902, 3897. So we might draw another one. Oops, gotta go back and reestablish my line. Insert. Sorry, I'm blanking on how to do it sometimes. So we might go over here and draw another one. This along this line then. So we would draw it here. So here's 3903. Here's 3897. So you can see we're maybe a little closer to the 3902 than the 3897, if I'm reading that right. And we would go on down. Here's a 3901 down here. pretty close to that one. And we would have another line. It should be closer to 3902 than the 3897. And what is the name of that lake? Rushberg Lake. That's Raspberry Lake. Yeah, Raspberry Lake right here. Raspberg Lake? Roseburg Lake, whatever it is. It's 98. And so, yeah, just using these lakes then as data points, you're going to draw a contour line across and 5 feet apart. So up off the side here somewhere, you would write then, if I can get that to move, you would write up here 3905. So that's, you know, the surface here is a little bit higher than that. So you'd have to dig down to 3,905 feet above sea level, and then water would fill the bottom of your hole. Here you would have to dig down 3,900 feet, so you'd write 3,900 here. And so then you're going to have 3895, 3890, 3885, 3880, and so on and so forth across the map, drawing those contour lines. Okay? So once you've done that then, you're going to answer question B, which is, in what direction does the water table slope, and what is its average gradient in feet per mile? So, gradient, how far does it drop in feet per every mile of run? So you're going to first tell me which way it flows, and then you're going to tell me how much slope it flows down. Yeah, it's okay to think of water tables as flowing down a gradient. Even though they're not a surface feature, they're a below ground feature, they do that. Then in question 1C and 1D, you're going to go back to page 167, and there you'll find Darcy's law. And Darcy's law is V, which is the velocity, the speed at which the groundwater is flowing. And then it's determined by K over P. And the K is well, let's start with the P. The P is the porosity. How many pores are in the sediment or rock that the groundwater is moving through? And then K is it's called the conductivity, but basically what you would think of is the permeability. In other words, how connected are the pores? So you might have lots of pores, but if they're not connected, and I've shown you this before, if they're not connected, you're not going to have much flow through them. Conversely, if you have pores and they are well connected, then the groundwater will flow more rapidly through them. Okay, so that's K over P. Then H over L is what you have determined in question question B. H is basically the height, and L is the length. So what's the height down, the drop in distance, vertical distance, that the groundwater flows over this map? So how much does it drop as it's flowing? And its length, and over what length does that drop occur? Okay, so that's Darcy's law. And so you look in the notes on here, you're to assume a hydraulic conductivity. That's a K of 1 times 10 to the negative 2, or 0.01 would be another way to write that. And an effective porosity of 20%. Of course, you can write 20% as 0.2. Okay, so those are the K and the P. And then you're going to convert your hydraulic gradient, what you determined in question B, into units of converted from feet per mile to feet per foot. Okay, so you have figured out how many feet the groundwater drops per mile of distance in question B. Now you're going to convert that to how many feet it drops per foot of distance in question C. And remember, there's 5,280 feet per mile. Okay, and so then once you've done that, that's going to give us a velocity, and the number should be in centimeters per second. That's what you will determine. How many centimeters, or more likely, what part of a centimeter does it flow per second? Okay, once you've done that, then you're going to apply this. Question D is if the distance between Ellsworth and Lakeside is 7 miles, so they're giving you a 7-mile distance, and they've converted that for you from 2 kilometers and then to centimeters. That's very nice. Okay, so that 7 miles is equivalent to 1.13 times 10 to the 6 centimeters. And you can feel free to write that out longhand if it helps you. How long would it take for the groundwater to make the journey from Ellsworth to Lakeside? So how long would it take the groundwater to move from here, the 7 miles, to here? And I want an answer in years, not in seconds, but I want you to convert it to years. Okay? That was fairly involved. I realize that, but give it a shot. And then lastly for this video, in question E, it talks about a windmill here. Now you notice here's a range line. So here's range 4, here's range 3. And this would be the township line. Notice the range line jogs a bit here. That's because if you remember, range lines are lines of longitude and they merge at the poles. So every so often they have to jog like this so that they can merge at the poles, but allow us to continue to have square parcels of land. Okay, so having said that, this question can be a little confusing. So the first part of the question, they're referencing this windmill right here. And the number next to it, so you see the sign for it right here. So let's zoom in on that just a little bit. Okay, so this is the sign for the windmill. And then this is the section number, so you know this is a mile on a side, so this is section 22, and this would be the southwest corner, because you always assume north is towards the top of the map. So this windmill is at 3,877 feet. Okay, and so that's for discussion's sake. But then they switch gears and they want you to go to section 19 in the next range over. So here, let me zoom back out. Okay, so if you see, so here's range 4 west, here's range 3 west. Now it's asking you for section 19 in range 3 west, and that's right here. Okay, and you know what? I need to go back, get rid of those lines because they're going to confuse things. Otherwise, there we go. So we'll go here, and let's zoom in on that a bit. Okay, so here's section 19. The question says, locate the windmill in the northwest quarter of section 19. Okay, and so that'd be this windmill right here. So maybe let's zoom in on it even a little bit more. So this windmill right here. And it says, how high must the water be raised by the pump to fill the stock tank? And explain your answer. So this is the surface elevation of the windmill. Previously, you will have drawn surface contour lines on here, which tell us the elevation of the groundwater table. The groundwater table, that's the surface of the water table, the wet area that you would find if you dug down in the ground here. And so you're going to have to estimate, come as close again, to whatever groundwater table line is here, and then paying attention to the surface elevation of the windmill. Basically, what's the difference between those two? That's how high this windmill has to raise water out of the groundwater to get it to the surface to fill the stock tank to water the cattle. All right, that's for the first 3 elements of the question and problem set for groundwater. Thank you.